Hello, welcome to the second AS Pure Maths revision video. In this video we'll look at trigonometry, vectors, differentiation and integration, and exponentials and logarithms. The next equation requires us to use a trig identity. Let's have a quick recap. If we have a right angled triangle with an angle x and a hypotenuse of 1, the height will be sine x, the base will be cos x. Applying Pythagoras, we get sine squared plus cos squared x equals 1. This identity we will use to convert this into a quadratic in sine alone. So we change cos squared for 1 minus sine squared. We rearrange the equation, and now we have 9 sine squared x minus 6 sine x plus 1 equals 2, which can be factorised to give 3 sine x minus 1 all squared equals 2. Part B asks us to solve the equation cos squared x equals 8 sine squared x minus 6 sine x, x between 0 and 360. We simply change this equation for the equivalent form that we created in Part A, namely 3 sine x minus 1 all squared equals 2. Using that equation, we take square roots of both sides and we get 3 sine x minus 1 equals plus or minus the square root of 2. So sine x equals 0.8047, in which case the angle x is 53.58 or 126.42. That's in the first two quadrants. Or sine x equals minus 0.1381, giving us two more solutions in quadrants 3 and 4, 187.94. and 352.06. In this trig question, we're asked to show that tan 2x equals 5 sine 2x can be written in the form 1 minus 5 cos 2x sine 2x equals 0. For this, we need another trig identity. Let's return to the triangle we had in the previous question. Here we can see that the tan of x will equal sine x over cos x. So the tan of 2x will be sine 2x over cos of 2x. So we write sine 2x over cos 2x equal to 5 sine 2x. We multiply both sides by cos 2x and rearrange it to get sine 2x minus 5 cos 2x sine 2x equals 0, which when we factorise it, taking out the common factor of sine 2x, gives us the form requested. In Part B, we're asked to solve the equation tan 2x equals 5 sine 2x. So that's equivalent to solving 1 minus 5 cos 2x times sine 2x equals 0. This is satisfied when either the first factor, 1 minus 5 cos 2x equals 0, so cos 2x is a fifth, and we can solve that to see that x is 39.2 or 140.8, or when sine 2x equals 0, in which case x can be 0, 90 or 180. Let's look at a vector question. We're given the position vector of 2 points, A and B. OA is 3i minus 7j, OB is 8i plus 3j. These are the offsets from a given origin O. We're asked to find the vector AB. We start at A, we have minus OA, it's the opposite direction to OA, plus OB. So AB equals minus 3i minus 7j plus 8i plus 3j. We simplify that to get 5i plus 10j. To calculate the modulus, it's simply Pythagoras, the square root of 5 squared plus 10 squared, which we can simplify to 5 root 5. If we were asked to find the bearing of A from O, by convention, I is the unit vector in the east to west direction, J is the unit vector in the south to north direction. So we add the north direction, we work out the angle alpha between OA and the horizontal, to be tan to the minus 1, 7 over 3, or 66.8 degrees, which gives us a bearing of 90 plus 66.8, equal to 156.8 degrees. Differentiation. You need to know that if you differentiate a power of x, you multiply by the power and you reduce the power by 1. We're given y equals 3x squared plus 6x to the third plus 2x cubed minus 7 over 3 root x. We have to find dy by dx. Our first job is to convert that into a differentiable form, a sum of terms that can be differentiated using the recipe above. We convert the 2x cubed minus 7 over 3 root x to give us 2/3 x to the 5 over 2, so that's x cubed divided by x to the half, minus 7 over 3 x to the minus a half. Now we're in the situation where we can differentiate term by term using the standard recipe. So here we differentiate the x squared to get 2x, so this becomes 6x. This term here we're going to multiply by a third, so it will become 2, and reduce the power by 1, so a third minus 1 equals minus 2/3. This term here we're going to multiply by 5 over 2, so that will give us 5 over 3. We'll reduce 5 over 2 by 1 to give 3 over 2. And finally, here we'll multiply by the power minus a half to give us plus 7 over 6. Reduce it by 1, so the power becomes minus 3 over 2. In this question, you're asked to differentiate from first principles. Fortunately, in the formula booklet, there's a definition of what it means to differentiate from first principles. Fx equals x cubed. F dashed x, the derivative of f of x, will be the limit as h tends to 0 of x plus h all cubed, that's the f of x plus h, minus x cubed, that's the f of x, divided by h. We expand out the cube term, and you see that the x cubed in the first expansion will be cancelled with the minus x cubed, and that will leave us 3x squared h plus 3x h squared plus h cubed. We simplify that. This becomes the limit as h tends to 0 of 3x squared plus 3xh plus h squared. As h tends to 0, the second and third terms will both tend to 0, leaving 3x squared. And that's it. You will also find questions using differentiation to identify maxima and minima of particular functions. Here we're told we have a solid glass cylinder with a volume of 75 pi cubic centimetres. We're told the cost of polishing the surface area of this glass cylinder is £2 per square centimetre for the curved surface and £3 per square centimetre for the circular top and base areas. We're told the radius is r, and we have to derive the formula for the cost of polishing. So assuming that the height of the cylinder is h, the volume will be pi r squared h, and we're told that's 75 pi. If we look at the cost, we take the top and bottom base areas, which will be 2 times pi r squared. We multiply by 3, as it's £3 per square centimetre for these areas. And we take the curved surface area, 2 pi r h, and we multiply by 2, as that's the cost for this area. From the first equation, we can cancel the pi's, and we can see that RH will be 75 over r. We can use that to eliminate h from the cost equation, and that will give us c equals 6 pi r squared plus 300 pi over r, which is what we wanted to show. Use calculus to find the minimum cost. So first of all, we differentiate with respect to r. We get dc by dr equal to 12 pi r minus 300 pi over r squared. At a minimum, this derivative will be 0. We can solve this to find r. It will be the cube root of 25, which equals 2.92. We take this value and we substitute it into the formula for the cost, and that gives us a minimum cost of £483.48. We're asked to justify the answer obtained as a minimum. So here we use the second derivative. So we get d2c by dr squared equal to 12 pi plus 600 pi over r squared. That will always be greater than naught, as both of these terms will be positive, and so this will be a minimum. If the second derivative is positive, it indicates a minimum. Here's another differentiation question where we're looking to find the equation of a tangent to a curve. The equation of the curve is y equals x squared plus 4 times x minus 3 all over 2x. We need to find dy by dx. The only way we can differentiate at the moment is by using this recipe. So we have to convert the equation into that form. We expand the brackets and then we divide each term in the expansion by 2x to give us x squared over 2 minus 3 over 2x plus 2 minus 6x to the minus 1. We can now apply our recipe for differentiating. We differentiate x squared over 2 to give us x. We differentiate minus 3 over 2x to give us minus 3 over 2. The constant term 2 disappears, and we differentiate minus 6x to the minus 1 to give us 6 over x squared. We're asked to find the equation of the tangent at the point where x is minus 1. So we substitute minus 1 into the original equation to get the corresponding value for y. That's y equals 10. We substitute minus 1 into the derivative to find that dy by dx is 7 over 2. So the gradient of the tangent will be 7 over 2, and the tangent will pass through the point minus 1, 10. The simplest form of the equation will be y minus 10 equals 7 over 2 times x plus 1. We're asked for it in a specific form. We multiply through by 2, rearrange the equation to get 7x minus 2y plus 27 equals 0. Integration. We're asked to find the integral of 2x to the fourth minus 4 over root x plus 3 with respect to x. So we want to use the recipe for integration, which is increase the power of x by 1 and divide by the new power. We rewrite the expression, so we have 2x to the fourth minus 4x to the minus a half plus 3. And then we apply the recipe to each of the terms in turn. So 2x to the fourth, we raise the power by 1, it becomes x to the fifth, and we divide by 5. Minus 4x to the minus a half, we raise the power by 1, so that becomes a half, and we divide by the new power, a half. And then 3 becomes 3 to the x, or 3 to the 1, divided by 1, and we add a constant of integration, c. Simplifying those terms there, we get 2 fifths x to the fifth minus 8 root x plus 3x plus c. Here's a common integration question. We're told the curve with equation y equals fx passes through the point 425, and we're told the derivative of f of x is 3/8 x squared minus 10x to the minus a half plus 1. We need to find f of x. So we integrate the derivative. We get f of x is 1/8 x cubed minus 10 over a half x to the half plus x plus the constant of integration c. We know that the curve passes through the point 425, and this is what allows us to work out the constant of integration. F of 4 will be 25. We substitute 4 into the expression for f of x. From this we can derive that c equals 53. That gives us f of x is x cubed over 8 minus 20x to the half plus x plus 53. We're then asked to find the equation of the normal to the curve at the point 425. So the gradient of the tangent at 425 is f dashed 4. So we substitute 4 into the expression that we've been given for f dash of x. That will give us 3 minus 10 over 2 plus 1 equal to 2. The normal is perpendicular to the tangent, and so the gradient of the normal is minus a half. And the equation will be x minus 25 equals minus a half x minus 4. We multiply through by 2 and rearrange to get x plus 2y. Minus 54 equals 0. An application of integration is finding the area under the curve. We're told that the line y equals 10 minus x and the curve with the equation y equals 10x minus x squared minus 8 intersect at 2 points A and B. First, we have to calculate the coordinates of A and B, which is a simultaneous one linear, one quadratic. So we eliminate y, we get a quadratic, we factorize it, we get the x coordinates of the 2 points, we substitute in the linear equation, and we get the y coordinates of the 2 points. The second part of the question is what we're really interested in, which says the shaded area R is bounded by the line and the curve, and we want to find the exact area of R. So if we draw the vertical lines, the ordinates from A and B, the area under the curve between those two lines will be the integral between 9 and 2 of 10x minus x squared minus 8 dx. But we need to subtract from that integral the area of the trapezium beneath it, and the area of that trapezium will be a half the height, and the area of that trapezium will be 7 times 8 plus 1 over 2. Evaluating the integral, we get 5x squared minus x cubed over 3 minus 8x between 9 and 2, minus 31.5. Then when we substitute 9 into this expression, we get 90. When we substitute 2 into this expression, we get 4/3. So the exact area of R will be 90 minus 4/3 minus 31.5 equal to 343 over 6. Our last two questions are related to exponentials and logarithms. We're told that the mass, m grams of a leaf, t days after it has been picked from a tree, is given by the formula m equals p e to the minus kt. So this is a typical exponential decay curve, which is showing the weight of the leaf as it dries out. And we're told k and p are positive constants. We're given various points on the curve. So when the leaf is picked from the tree, that's at t equals 0. Its mass is 7.5 grams. So we substitute t equals 0 and m equals 7.5. We get p is 7.5. We're also told 4 days later, so when t is 4, its mass is 2.5. So we substitute these into the equation. We get 2.5 equals 7.5 e to the minus 4k. So e to the 4k will equal 3, and therefore k equals 1/4 ln, the natural logarithm of 3, which is what we're meant to show. And finally, we're asked to find the value of t when dm by dt equals minus 0.6 ln 3. So when we differentiate m, dm by dt will be minus kp times e to the minus kt. We substitute the values for p and k into that expression, and we want to find the value of t when this equals minus 0.6 ln 3. So we've got this equation here in t to solve. We can cancel the ln 3 from both sides and simplify the equation to get e to the minus ln 3 over 4t equals 0.32. Take the natural logarithm of both sides to get minus ln 3 over 4t equals ln 0.32 equals minus 1.139, and therefore t equals 4.15. Our last question involves solving equations with exponentials and logs in them. Here's the first one. 5y equals 8. We need to find y. Log to the base a of x answers the question, which power do I have to raise a to get the value of x? If 5 to the y equals 8, I can take log to the base 5 of both sides, and this will give me y equals log to the base 5 of 8 equals 1.292. If I don't have log to the base 5 on my calculator, I can use the recipe inside the formula booklet, which allows me to change the base of a logarithm. So in that case, I can write y equals log to the base 10 of 8 over log to the base 10 of 5, using this formula from the formula booklet. And I'll get the same answer, 1.292. The second part of the question is a log equation. Here we multiply through by 2 and take the logs to one side. This gives us 2 log 2 x plus 15 minus log 2 of x equals 8. 2 log 2 of x plus 15 is the log of x plus 15 squared. When we subtract logarithms, we do a division. So when we subtract log 2 of x, we get log to the base 2 of x plus 15 squared divided by x. That equals 8. That tells us that x plus 15 squared over x must be 2 to the power of 8. That gives us a quadratic in x, which we can solve by factorisation and get solutions of x equals 1 or x equals 225. That's all, folks. I hope you found it useful. If you haven't done so already, take a look at part 1, which covers various algebra problems, coordinate geometry, the factor theorem, and the binomial expansion. Good luck in your exams. Bye-bye.